My name is Asad Mirza, PhD candidate here in the BME department. And this is the second part on my MATLAB image processing presentation on behalf of the MBS. So, without further ado, let us begin. So, first things first, let's talk about the concept of noise filtering. So, in order to remove noise from an image, the first thing that you'll probably run into is something called the Fourier Transform. And the Fourier transform, at least in a 1D sense, which is how you'll usually see it, refers to turning something that's time related, so a time signal, into what's called its frequency components. And the way it works is, let me see if I can restart this little animation thing. So if you had a time signal, like so, and it was oscillating like this. You can see how parts of it are wavy, parts of it are a bit more straight. You can think of this time signal curve to be made up of multiple sinusoidal waves, each with a very specific frequency that it's oscillating around. And if you just add all these frequencies up, you get the time signal. If you have the time signal and you extract what the sine signals were that make it, then you get your frequency spectrum. And here's a better image that encapsulates this. If you had time signal here, this amplitude could be voltage, it could be temperature, current, just some time signal of some sort. And you see it oscillating over time. And if you were trying to represent this curve as the summation of more simpler sine curves, you would be able to recreate this curve using only a single sinusoidal curve of a very specific frequency and just combining all those frequencies together. So maybe this curve here, it behaves a little bit like the red curve, it behaves a little bit like the gray curve, and it behaves a little bit like the green curve as well. And if you combine all of these, you make up the purple curve. But if you were to sort of shift your view, this red curve is oscillating at a very specific frequency, same with the gray, same with the green. So in one way, this is the time version of the signal. This is the frequency version. They are both exactly the same. They're just looking at your data in a different angle and different view. So mathematically, the way you do this is with a complicated exponential, but you don't really need to wrap your mind around the deep parts of this. You can easily take an entire course on just how Fourier transforms work. But just like how we extracted the frequency spectrum of a time-varying signal in one dimension, you can do this in 2 dimension on an image. But now, instead of just doing summation of your signal with this exponential once, you have to do it 2 times, one for each dimension. And what would that look like in terms of like an output? Because the output here is very easy to see. You have your time signal, and you have another signal that just shows you spikes wherever your frequencies are most important for your signal. But for an image, the best way to show it would be just give you a little example. So this is the letter A. It's a very low and blocky A. But if I were to do a Fourier transform of it, you would get this. And the Fourier transform is always based around the center and is radially symmetric. So the most information is near the center, and the least amount of information is on the edges. So if you wanted to filter some part of this signal, then you would start from the center as your XX as 0, 0, so 0 Hertz in each dimension. And you could go around this image and just keep certain blocks of this image, depending on if you want to filter out maybe like this ring here or a spot right here or a spot right here. And this is how you can keep only a couple of frequencies. And the way you can tell MATLAB how to keep, like, for example, everything that's within a certain distance of 0, you can just use Pythagorean theorem, where you have a point xy, you have your center, and you just find the distance between them. And if you have these distances, you can make a graph like this, where starting at the center, as you go off from the center, you have distances that are 4 units away, positive and negative in U, and positive and negative in V. And then here's a color grading that shows you how far away you are from the center. So what would this A image look like if we only kept the information, let's say, right here in the center? Or what about if we only kept the information right here in the cyan region? Or what about if we kept the information from everything in this yellow region? Or what if we kept everything all the way come to the red region? Let's investigate. So if we only kept the information right at the center, well, we see something. It's not exactly the letter A, but it's something. And this would be the representative information in the image space, and this would be the Fourier transform of it. Now, if we kept everything up to the cyan, well, we can sort of start making out the letter A, but not quite. If we kept starting maybe a little bit into the yellow region, we can better make out that this is maybe has like an arrow tip here. Maybe there's something going on in the center here. And if you kept a bit more of the Fourier transform space, you can better see that this probably is an A of some kind. And by the time you get everything but the edges, you most certainly have recovered the image. And that is the gist of how you can do a Fourier transform on an image. So before I continue on how to do it actually in MATLAB, any questions?
And so that would also be for color images, or since it's black and white, you need to convert it to black and white.
Oh, if you want to do it on a color image, it's a bit more difficult, but it's the same process. Because this is done in 2 dimensions, a color image is inherently 3-dimensional. Well, actually, it's 2, 3. Yeah, it's 3-dimensional. So you would have to do it one for the green, one for the red, one for the blue. So it's easier if you just work in grayscale, because then you just have a 2D matrix, easier. So how do you do it in MATLAB? So it's really laughable how straightforward this is in MATLAB. So you use the IMRead function to read your image, whatever it is. Preferably this image is grayscale. And let's say this was your image right here, a little square block in an image. You can use the FFT2, which is the fast Fourier transform, 2-dimensional, pass your image. Now, because of the fact that this is radially symmetric, you're going to have to want to shift everything to the center, which is what this FFT shift does. And the next thing you have to do is, by nature of how the Fourier transform works, it usually shows you very large and very small values all on a single graph, and that can really distort how the image looks like. So the easy way to fix that is if you just look at the absolute values and then you log everything, so the numbers that are very large and very small become comparable to each other. It's just a change of how you visually see it. And then you can just pass this FFT image to IMShow. And then if you use this open brackets, this displays the grayscale of the image. And what ends up happening is if you have a little white block here, the Fourier transform of it looks like this on the right. Oftentimes, it's very difficult to have a Fourier transform of an image and being able to like just immediately tell what the inverse is because of how just strange it looks like. You would never expect that this weird repeating pattern here is actually this little white block in a real image space. Point and point. So let's go ahead and check this out in MATLAB with some examples here. So if I were to show you this image right here, so I'm going to go ahead and do IMShow I. This is an image of a nice and beautiful little doggy, a little puppy. And just based off of this image, remember that when you do Fourier transform, just like when you do it in the 1D sense, it tries to look for sinusoidal patterns in an image. So is there anything in this image that looks like it has a pattern to it?
Yeah, the checkering on the floor.
Yeah. So interestingly enough, if there is any part of your image that has a pattern that repeats, even if you can't really tell how it repeats or what exactly the relationship is of the repetition, if there is something that looks periodic to you in the image, the Fourier transformation will emphasize that periodicity very well. So this is what I mean. So you do FFT2, shift it, log of it, and then you plot it. So let's go ahead and do a comparison. And you can see here we have these sharp spikes and these lines extending from the center in a star pattern. These sharp spikes here actually are what make up the pattern that you see in this image. And where is the dog itself in this Fourier transformation? It's probably all the other stuff besides the very prominent values. Because anything that is repetitive in your image is very emphasized in the Fourier transform, so it shows up as bright in Fourier transform. Anything that is not very repetitive in your image shows up as the equivalent of just random noise in your Fourier transform. Does that make sense? All right, so that's how you can identify one or the other. So how can we leverage this fact of periodicity and patterns to remove noise? Well, what we can do is actually remove noise in an image as long as it's what's called periodic. So periodic noise can come from electrical, electromechanical interference when you're doing image acquisition. And the important characteristic of periodic noise is that it's independent of spatial coordinates. So the noise that you see in one part of the image should be the same as in another part of the image. It doesn't actually depend upon where you are in the image. It seems to have a pattern that repeats everywhere. And this pattern, because it's repetitive in the image space, will really highlight and show itself in the Fourier frequency space. So let me just go ahead and show you this. And this is the closest thing to pretty much movie magic I've ever seen. And I always like to show it. So if I have this image here, and let me once again show it to you. I am show I. This is an aerial photography image, and you can see it's an image of this field with houses and lakes and such, but there appears to be this checkered pattern thing overlaying the image that we can't see through. So let's go ahead and do a Fourier transform of this and then see how this looks like in the frequency space. So does anybody see what might be causing these stripes or anything or something in the frequency space? You might have to zoom in a little or squint. None? Well, let's take a look here. If I zoom in on the center, do you see these bright dots right here?
Yes.
Yep, those are actually what's causing these lines in our original image space. And in fact, because of the periodicity of the Fourier spectrum, these dots are actually repeating at a very specific frequency as you go along X and Y. Bye-bye, Catherine. That's fine if you have to leave. All right, so continuing on. So yeah, it repeats at very specific intervals. And because it repeats very nice and symmetrically, we can actually leverage this and remove it from an image using some clever techniques. How do we do that? Well, remember how I said we can take the distances of the image? Well, let's do that for this. We take the distances of an image, and we can see here we have 0, 0 in the center. We have positive, negative, roughly 600, positive, negative, roughly 400 in the Y. And we can tell MATLAB, okay, keep everything in the image except for the small little band that contains those bright dots that we want to remove. So what would that look like? Well, we can just do a little filter here. And if we do the little filter, we can tell MATLAB, okay, if the values are, let me see if I can do this side by side. If the values are less than 98, keep the image as is. If the values are greater than 103, keep the image. But if it's anything between these two values, meaning it's this black part right here, make it 0. And the part that I'm making 0 are right where those bright little pixels were. And then what I'm doing is I'm doing the inverse Fourier transform, and then I'm plotting the output. And what you can see here is we've removed those 4 bright spots, and we have suddenly removed that periodicity noise that was in our image. And now it still might be viewable in our image because all we did was remove the 4 brightest ones. But if we zoom in here, there are still like these 2 here and these 2 here. So if you wanted to really get rid of it, you would have to do numerous of these circles to get rid of all of them. But for a first pass approach, this really does clean up the image well. Any questions?
Yeah, the reason why it's concentric circles is because the Fourier transform involves the frequency pattern of the whole entire image.
Yeah, so because the Fourier spectrum is symmetric and it's based off sines and cosines that have a nice periodic frequencies, everything you see in a certain XY position is always going to repeat circularly. And that's also why we did the FFT shift, so everything shifts to the center. Otherwise, it was going to be in the 4 corners of the screen, and you wouldn't be able to do the filtering as nicely.
Interesting, thanks.
It's basically just a property of trig that's going to be like this.
Good to know.
So now if we do a compare and contrast, here's our before with the sinusoidal frequencies and periodic noise. And this is after we've just removed the 4 brightest spots of the image. Now you can actually make out the lakes, the houses, and everything. So really powerful stuff. So just to highlight this a bit more, let's say you want to take a look at what's going on in this part of the image here. So if I zoom in on this part, can't really tell what's here. But if I zoom into the same part over here, now I can see we have like a ditch here, some trees probably, highway, easier to tell. So that was periodic noise. Any questions before I continue?
If you only have it repeating on one plane of direction, not just throughout the entire image, like when you have like a rerun or like a VHS tape,
something like this, something like that, probably.
Yeah.
Yeah, as long as it's spatially independent, so like it repeats from bottom to top everywhere in the image, and it's not just like localized, you'll see it in the frequency spectrum.
Okay, great.
It might not be as nice as like a little couple dots here or there. It might be like 2 dots here, 2 dots here or something. Or it might be like a weird shape here and a weird shape here. But you'll be able to easily spot it in the frequency space.
Okay.
Next type of noise that we can deal with is called salt and pepper noise. These are also called impulse, spike noise. They're like raininess in your image. They usually show up as a random scatter of white or black pixels. And if you've ever seen like white noise in an image or a TV signal, that would count as salt and pepper noise. And the way to remove this noise is fairly interesting. So if you take a look at a regular image, the values are gonna range from 0 to 255. So values that are closer to 255 are white, values closer to 0 are black. But for the most part, images are between 0 and 255. It's very rare that a specific part of an image is exactly 0 and exactly 255, but salt and pepper noise is always exactly 0 and exactly 255. So we can leverage this fact and do what's called a median filter to fix it. So the idea behind the median filter is if you take a look at any subset of pixels in an image, and you sort of emphasize it, and then you take a look at what the values are, you'll see values between 0 and 255, and everywhere where you see the salt and pepper noise, you'll see it as a big 0 or a big 255 that is completely not related to the values around it. Real images have smooth transitions, so the salt and pepper noise really sticks out. And so what you can do is do what's called a median filter, where for every 3x3, 2x2, 4x4, 5x5 block of pixels, you take the median of those values in that block, and you replace the center value with the median. And if you replace it with the median, the values that are 0 or 255 automatically get shoved to the sides, and the median value, which is probably going to be one of these more normal values is going to be used to replace it. So if, for example, you looked at this space right here, this 205 to this 205 here, and you ran a median filter on this 0 would get shoved all the way to the left here. 205 or 208 would get shoved to the right, and the median value is going to be 204. So that's where you're going to be putting in this spot right here. And like this, you can go across this entire image and remove the salt and pepper noise. So just to show you how effective this is, you can have an image, let's say this rice image, and if you add noise to this image using the IM noise function, and I'm going to add 70% noise right here. So all of a sudden you have all this salt and pepper noise that, and you can't even tell that this image had rice to begin with. It looks just like static. So what if we do this? So if we do this median filter, I'm going to do a 9x9 grid, meaning I'm going to take a subset of 9 pixels, and I'm going to find the median of these 9 pixels and replace the center with that all throughout the image. So if I do that, I'm just going to do the medfit2, pass it the image, the 9x9 matrix. And now you can see here, this probably doesn't look like rice per se, but it looks like something at least. And this is a severe case where 70% of the image was noise. But look how well it recovered the image. Now, if we want to better see it, maybe your image only has 20% noise, let's say. If it was 20% noise, then yeah, you can probably tell that it is rice of some kind, but there's something in the image. And if I now try to do the median filter, pretty much it got rid of all of it. All the white salt and pepper noise disappeared. And in fact, the smoothing averaging was almost too extreme. So now you can perhaps dial this down, maybe a 3x3. And now we've recovered more of the image, but now it's missed some of the salt and pepper noise. Maybe 4x4 would be better. Maybe that is. So this way, you can use the median filter to get rid of the salt and pepper noise. So before I continue, any questions?
Yeah, what is it measured in? Because it's from 0 to 255 approx. Is that like the pixel format of that like kind of white black scale?
Yeah, so grayscale images by just imaging convention go from 0, which is black, to 255, which is white.
Thank you.
It's just how images are the standard. I don't know specifically why. Actually, I think it's 0, 255 because of some byte reasoning or something. Like it's handy to some power. I forget the details.
PCB8?
I think so. Yeah. I think that's it.
Thank you.
Yeah. So yeah, that's noise removal for salt and pepper noise. Next thing I want to highlight, if you're interested to learn more about image processing, you can take EL 5820. So this will tell you about image fundamentals, transforms, image enhancement, edge detection, segmenting images, how to identify textures in an image, how to restore parts of an image. And then you can also learn how to do image compression. So like how does JPEG work, for example? How do you compress a very gigantic image to a very small size, but retain the quality of the image? And the only prerequisite is that you pretty much know a programming language to do all this in. Examples would be like Fortran, Pascal, C, Python, MATLAB. Any of them, you just need to know a programming language. So you can take this course. It's naturally a 5,000 level course, meant for grad students, but you can take it as an undergrad as well. And even higher than this, you can take 6821, which is computer vision, which goes beyond this. So you can do image formation properties, brain topography, color vision, how does the brain see images, statistical patterns and classifying things in an image. Stereo vision, so how does like one viewpoint or two cameras see the same thing from different angles, and I can leverage that to figure out details or properties of an image. And how you can figure out motion vision from this. Same just as before, except you're gonna have to have already taken image processing before you take this. And you also gonna need to know programming language. I have taken both these courses. So they're taught by Dr. Malik or Dr. Ajadi. And he's in the BME department, but he's also in the electrical engineering department. Great guy, very laid back. Any questions on these two before I continue?
Yeah, they said they're only available for combined students, if you remember.
I forget. I think the image processing is combined because back when I took it, there were undergrads in it.
Okay.
So maybe there was like an override or something. Maybe, I forget. So yeah, that's that. So that was the end. Oh, slide. This would have been part 2 actually. And when I made this slide, it was actually meant for like an afternoon section of demos. I'll just go right into all the demos right now. So I have 3 demos prepared for you guys. I use up everything we've learned from part 1 and 2. So I have breast microcalcification detection, fingerprint recovery, and how to extract fluorescent signal from a video. So do you guys have any preference on which one you want me to start first or anything, or just go sequentially?
Fingerprint recovery sounds cool.
All right, so we'll first go to fingerprint recovery, then we'll jump to breast microcalcification, and then the fluorescent signals. So, fingerprint recovery. Issues with fingerprints is that they're highly detailed, pretty much unique to everybody. They're fairly difficult to alter or fake. As far as I know, they're durable across a lifetime, so the ones you have once you've grown up are pretty much what you'll have. But the main difficulty in fingerprint analysis is that it's very dependent on how high quality of a print you can get. So here are some aspects of a fingerprint that would be like identifying marks. So you have forensic people have like named these little features. So they have like termination, bifurcation, links, ridges, spurs, crossovers. And if you can find enough of these in a fingerprint image, probability states that they're going to be unique to you and only you. So the issue comes when you have to try to do these prints from people, and they have like a dry fingerprint, let's say, and then you don't really see these details well, or maybe they're too wet of a fingerprint, in which case some of the features get smudged over, or maybe they applied too much pressure when they were collecting the fingerprint, or maybe they didn't apply enough pressure. So the chances of you getting a perfect, nice fingerprint that has nice qualities is actually fairly lowish. So if you can figure out an image processing algorithm that takes any of these and tries to recover the maximum amount of detail in the image such that you can recover all these features, that goes a long way in helping identify that if this fingerprint belongs to a certain person. So what are we going to do? So here's an example of a degraded fingerprint, and we're going to see if we can extract as much information of this, as much of the details from this image as possible. So here are some of the helpful functions you might want to use. A lot of them are highlighted in part 1 or part 2. And yeah, so we can go ahead and use these to figure out how to extract the details of this fingerprint. So let's go ahead and try this out. So first off, let's see the original image. Nice and degraded. You can sort of see maybe there's like a bifurcation here, or maybe just a spur. Can't say for certain. So first thing I'm going to do is I'm going to adjust the contrast. And if I adjust the contrast, now I can better make out some of the details here of the image. Next thing I'm going to do is maybe histogram equalization. If I do histogram equalization, maybe that helps a little. Difficult to say. If I do a median filter, maybe the median filter will get rid of all this extra little noise I see in the image. And it seemed to work a little bit well, but we could do more. Next thing I'm going to do is I'm going to blur the image slightly. So all that noise in the background, it will sort of blur and disappear, but any features in the image will get emphasized. So now all this in the background disappeared, and all I really see are more of these lines. So we're getting there. Now I'm going to do what's called binarizing the image. And by binarizing the image, I turn it from grayscale to black and white. And now that it's black and white, I can better make out what's part of the actual fingerprint and what's not part of the fingerprint. Next thing I'm going to do is what's called skeletonizing the image. And skeletonizing the image tries to fit a skeleton to your image based upon what's black and what's white. So now you can better make out what the actual image is. And if I compare it to before and after, you can see here that it's gotten rid of everything that was sort of in the periphery here, and we really recovered a lot of the actual fingerprint. And just as a comparison, here's what we recovered, and then here's what was the original image. So some major features that we might have been able to now figure out would be things like, so we have this branch here, which would have been this part right here. We have, let's see what else. We have this region right here, so which is this little island right here. So it's not the best recovery, but it's a start, I suppose. And here's another way you can view this image as a color difference. So this is another way you can view the image. So this really highlights the differences between the original and the recovered. And this is not the best recovery of the fingerprint, but there are many ways you can go about improving the recovery, as many people, if you like just do a quick Google, have tried using more sophisticated methods. Any questions?
Yeah, so you said there might be other approaches, like maybe doing some salt and pepper removal, or if there's something close to that.
Yeah, so I did do a little bit of the salt and pepper removal with the median filter, but there are other types of filters that would be better targeted for fingerprints, depending on how the noise is distributed. But it's really just, you have to go really in sort of a niche field to figure out what's a specific type of noise and how to emphasize the parts of the fingerprint details that you care about and what combination of functions are specific for that. Yeah.
Thanks.
All right. So that's fingerprint. Let's go over to breast calcification. So usually when you have a mammogram done, you can detect the level of calcification density. And because a mammogram is going to inherently measure the density of your tissue, you'll easily be able to spot calcification growth as white splotches that occur in the readings. And they're usually categorized as 0 to 6. So usually if you see a category 0 to 2, 3-ish, then it's probably benign and you won't have to worry about it. But if you get into a 4, 5, or 6, then that might be suspicious and you're going to have to deal with it. The issue is usually these calcification detections only really work if they're really large, but they usually start off as really small little microcalcifications and grow from there. So how do you spot them? Well, if you have a mammogram image here, you can spot these little microcalcifications as bright spots that show up in your image, but they're really small and you have to have a detailed eye for it. However, usually when you get these mammogram images, they might have noise in them or they might be a bit of movement artifact or something. So how would you restore this image to figure out if there are any microcalcifications? Because as far as I could see, there might be, there might not be, but it's hard to say for certain. So what we can do is maybe some Fourier transformation, some median filtering, some frequency spectrum filtering, see what we're dealing with. So let's go ahead and try this out. So we have our image. And if we see if we can remove the periodic image, the periodic noise from this. So on the upper left here, we have the original image. On the right here, we have our frequency spectrum. If we take a look at the frequency spectrum, you'll see the pattern that we found in the image are these bright dots in our frequency spectrum space. And what we can do is we can do a rather aggressive filter and remove everything that's in this circle. Or this is a square, but treat it as a circle and remove everything in it. And if you do that and do the inverse, we'll end up with this image, which is a drastic improvement to what we had before. So now we can do a salt and pepper noise removal to get rid of all this graininess in the image. And if we do that, we go from the left to the right, and now we can better make out the beginnings of these little microcalcification nodules that we're seeing here, or possible microcalcifications. And now if we could do a compare and contrast, here's the original image on the left and what we recovered using just two techniques of Fourier Transform filtering and then a median filter. And if we compare it to the original, we can see the original has a very clear microcalcifications right here, 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 all the way here. And in our recovered image, we can see these spots here. These sort of got recovered over here as well. Some of these smeared together, but we were able to recover some amount of them. So yeah, that's a technique that you can use as well. Any questions? No? All right. So the last thing I want to show you guys is fluorescent signals. So various biological signals can actually be recorded by staining cells with specific dyes. So you can have like a dye that is sensitive to voltage changes, a dye that's sensitive to calcium changes, and so on and so forth. And the idea is, if you have biological activity, you can measure how the color changes in your cell based off the intensity of these voltage, calcium, or whatever changes. And you can extract them onto a graph over time. And if you have a calibration that you know of, for example, let's say that you know for certain that this amount of brightness corresponds to this much voltage or this much calcium signal, then you now have a way to convert your image intensities to an actual measurement that has real world units. And now you can measure things like voltage over time, calcium over time, some other signal over time, just from your image. And usually combined systems that do this automatically are like $10,000 to $100,000. Some popular examples are like the MyCam, which is meant for voltage imaging. You have Photon, which can do like calcium imaging. And this is an example of, I believe, a rat brain, where parts of it are being stimulated. And the parts that are being stimulated are each being tracked with these little dots here. And each of these dots correspond to a different graph here. You can see how each of them start off or stop and sort of plateau after the stimulus ends. Now, what we're going to do is, if we have a raw video footage, can we extract the fluorescent signal from it? The answer is yes, naturally, but how do we do it? So some helpful functions for us this time around are going to be the video reader, which is from the computer vision toolbox. We're going to use RGB gray naturally. We're going to use this thing called IM Eclipse and then create mask. So let's see how we do this. So not this one. There we go. So we have our video, which is, I'm going to open this outside. So this is a video of some arteries undergoing calcium stimulation. And you'll see them in the image as bright spots that sort of appear and disappear. We're going to see if we can track these over time. So first things first, we're going to want to load this into MATLAB. You can use the video reader that reads in the video. We can extract a number of frames. And then I'm going to use a neat little MATLAB function called a weight bar and load in the image using read. And every time this loop runs, this weight bar is going to tell me it's loaded this image out of this many, just so I know that it's not stalled or anything. And I'm going to save this into a nice gigantic cell array for use later. So let's go ahead and run this. And it's loading the frames out of 8,999. So while I wait for this, any questions?
Yeah, I'm a bit confused with the fluorescence one. We actually need to get the video, and from the video, we're going to extract data regarding calcium values.
We're going to extract information regarding the intensity of a particular part of it over time.
Okay.
And the idea is, usually the person who's doing the research would have a calibration standard that they know, oh, this fluoresces this at this intensity and at this concentration, and they can use that to convert from fluorescent units to actual real world units afterwards.
Got it. And so those would be intensity values or lumens.
Yeah, luminance, intensity values, basically just tracking the color change of a group of pixels over time.
Okay, got it. Thanks.
So if we were to now view these images, we have this frame out here, and each spot in this matrix here is each of our images over time. And we have 8,999 of them for each of the frames. And if I take a look at every 50th frame, you can see here, image intensifies, gets dimmer, intensifies, gets dimmer as I'm going through the frames. And because there are 8,999 of them, it's skipping through them really quickly. This sort of highlights what we're going to try to do. So let's say, for example, we're going to try to get, what's a good part of this image that's changing rapidly? Let's say this part right here. So it gets dim, then it gets bright, then it gets dim, then it gets bright. So just to remember, this spot right here. All right. So I'm going to Control C out of this. So the first thing we're going to do is we're going to try to subtract the background from this image. And the reason for that is the background part of the image here doesn't really contribute to the part that's dynamically changing. So let's just subtract everything to have everything sort of at a 0 value we can relate to. And the way we do that is we grab a part of the image that isn't changing. So this corner right here, let's say, and remove the background from all the images. And now what we're going to do is going to use this handy little function called IMEllipse, and we're going to draw around the region that we care about that we're going to average out. So I picked the 120 frame, and if I remember right, it was this region right here, I think. So draw a little ellipse here and double click. And what it did for us was it made a mask into this function right here. And this mask is just a bunch of zeros with ones located wherever that block is located. So it's easier if I do IMShow cell int. Yeah, it's in that little region right here. So a bunch of zeros and then 255. And what we're going to do is anywhere where this white is in the image, I'm going to extract the values of it and find what the mean of them are for each frame. And then I'm going to make a time vector that has each of those values over time. Done. And now I'm going to plot it with just a straightforward t versus the trace. And I'm also going to plot what the smooth version of this looks like by using the smooth function. And if I do that, we get this. So that little white circle has this intensity changing over time. So it looks like it's some value and then there's a spike. Some values sort of changes, and then a spike again over here, and then changes as well. And the moving mean I applied might have been a bit too aggressive, but you can see that now you can track the raw fluorescent signal over time. And if you knew for certain that, intensity in my fluorescent signal of this much corresponded to this many millivolts or this much calcium, then you could convert the y-axis to those corresponding units and then use them for whatever analysis you're interested in. So that's that. Any questions?
Yeah, you would need some literature references in order to get those direct values if you want to extrapolate, let's say, calcium or let's say voltage.
Well, better than literature reference would be having a calibration standard in your lab, because usually these fluorescent signals are really microscope specific, dye specific, camera specific. So it would be better if you have, let's say, a certain sample of polymer or something that if you hit it with a wavelength of light that you know for a fact that it's gonna fluoresce with this much intensity, and you know that that's gonna correspond to this many volts or something for certain, because it's standard. Yeah. So that's how you would use it to convert.
Thanks.
No problem. Any other questions? Naturally, I'll be giving all the codes and the videos and PowerPoint over to Alejandro, and he'll upload it to YouTube along with everything else. So don't feel like you missed out on anything. So yeah.
Thank you. This is really useful. Thank you.
No problem. All right. If there aren't any other questions, I guess we're done.
All right. Hope you guys enjoyed it. Thank you, Asad, for showing this presentation, and hope you guys can apply these concepts to your MATLAB code. Take care, everyone.
Bye. Thank you.